Hey, what's up, guys? This video, what we're going to be taking a look at is how we're going to use some of the things that we've been studying with integration and calculus and how it relates to position, velocity, and acceleration. We have previously understood that the position function and velocity and acceleration functions are related to each other in the fact that if I take the derivative of the position function, I get velocity, and if I take the derivative of velocity, I get acceleration. Well, now that we've understood that integration is taking an antiderivative, we can go from an acceleration function back to a velocity function and back to a position function and answer various questions based on them. And so that's essentially what we're going to be looking at when we're in this particular section. And integration is often used when you're trying to when you're trying to evaluate a rate of some kind. So let's go ahead and jump into it and see what we have. So first, there's some vocabulary. Okay, obviously position is generally referred to as s of t, but sometimes it might be x of t. That just tells you where it is at a particular time. Average velocity, the two outputs that you're looking at, essentially your difference formula for your slope, y2 minus y1 over x2 minus x1. The instantaneous velocity is where we're starting to get the derivative. Instantaneous velocity in this case would be the derivative of the position. So whatever the derivative of the position is, that's how we get the instantaneous velocity as opposed to the average velocity. And speed and velocity are pretty synonymous with each other. However, velocity can indicate a direction and speed doesn't. So speed would, of course, be the absolute value of velocity. And here, acceleration being the second derivative of the position function or the first derivative of the velocity function. That tells you how fast something is changing over time. Where you're going from 0 to 60 in however many seconds. And it'll also tell you the sign of the velocity will tell you if the acceleration is increasing or decreasing. Just based on our relationship with the first and second derivative tests, things like that. Displacement here, the difference between the distance from where you start and where you stop. Displacement in this case can take into account negative areas. Okay, so if you think about it, maybe on a number line. Okay, so here you're starting maybe at like your front door or your bedroom or like your bed or like me, where my desk is. I start somewhere and then I walk so many feet this way, but then I have to walk back so many feet this way. So if I walk 10 feet this way and 3 feet back this way, my overall displacement is 7 feet because it can take into account things that would be negative. So we may see it maybe represented as like something like this, where this is positive, this is negative, this is positive, indicating where we're moving right versus where we're moving left. So that's the displacement. It basically tells you where you're going to end up from where you started from. Now that doesn't mean the total distance that you may have traveled. That is going to be the absolute value of the function, whatever it happens to be. So in this case, going back to the analogy that I had a second ago of somebody walking, if you go this way, oh wait, let me start over. There we go. All right, my horizontal line isn't very horizontal, but we're going this way. We just make his arm super long, 10 feet, and then we go back this way 3 feet. Well, the total distance that you traveled is 13 feet, as opposed to the displacement, the difference between them of 7. Sometimes the displacement and the distance are the same. It just kind of depends. Free fall motion here is something that you've seen in lots of other classes, Algebra 2, Physics, This is just going to describe, imagine you throw something somewhere, you take something and you throw it in the air. Ugh. Well, it follows this kind of parabolic arc when you throw something up in the air, and we wind up with a function like this where g is a gravitational constant of whatever planet you're on, in this case Earth. So we have our gravitational constants of 9.8 meters per second squared, or 32 feet per second squared, and v naught is your initial velocity, and s naught is the initial position. So that kind of covers the vocabulary that we would be looking at. And let me just go back here for just a second, because I'm not sure if we saw something here. The gravitational constant, usually we think of them as negative, but I guess they're putting the negative sign here to indicate it, because gravity is pulling you down, so it's indicating a direction that you're going. But anyway, let's take a look. An object moving along the x-axis so that its velocity at any time t is greater than or equal to 0 is given by the velocity function 3t squared minus 10t plus 3. And the position of the particle at time equal to 1 is x is equal to 3. So find a position function for the particle. So since they're giving us the velocity function, understanding velocity is the first derivative of position, I can say the antiderivative of the velocity function will be equal to the position function. So here we take the antiderivative of the function that was given to us. What was it? 3t squared minus 10t plus 3 dt. So if you take the antiderivative of all of those things, we're going to wind up with a t cubed minus 5t squared plus 3t and some constant of integration. And I don't know why. I know I don't have the greatest handwriting in the world, but my C's have been looking particularly ugly lately. But anyway, so that would be the position function. Well, if I want to know what the specific value of C is in this case, we can take the values that they're given this and substitute them. So we can take this one, let me go to a different color here. We can take the 1 that we have, and I can plug it in to my position function for t, and actually figure out what the value of c is going to be. Okay, and in this case, the x value is what essentially we would make the function equal to. So this will give us 3 is equal to, what do we have? 1 cubed minus 5 times 1 squared plus 3 times 1 plus the constant of integration. So 1 minus 5 plus 3 will give me a negative 1. So 4 would be equal to c. So find the position function. So the final function that we're looking for is, I'm going to take this c value here and I'm going to stick it into the c that I have here. And the final expression that I would look at for my answer for this problem would be s of t will be equal to t cubed minus 5t squared plus 3t plus 4. And there is your position function, where we had to use the antiderivative of the velocity function to get the expression, take the values that they gave us for the time interval and for what it should be equal to at a certain time, and find the constant of integration, in this case to be a value of 4. So find the displacement. So the displacement is again going to be the total distance that it has moved. So displacement in this case is essentially the definite integral of the function. So in this case, we're going to be looking at the definite integral from 0 to 6 of the velocity function vt dt, or v of t dt, and see what we end up with. Uh, you can think of it as, you can do the antiderivative for what we have here, but essentially we've done that, so you can think of it as s of 6 minus s of 1. Whichever way you prefer to do it, you can work at it from the original integral from 0 to 6, but we've already kind of gotten that, where we're kind of taking that 4 value there. So we can, let me just, another color I can take. I wanted a different color. We're taking this and we can kind of stick it in here for the integral, but essentially that's all we're doing here. So either way, let's go ahead and see what we wind up with. I'm going to just say s of 6 minus s of 1. So s of 6 will give me, not t, 6 to the third power minus 5 times 6 squared. And guys, for this, use a calculator. Don't try to do all this stuff discretely on paper or in your head. Use a calculator for this type of arithmetic. Plus 3 times 6 plus 4. And now we subtract the 1. Nope. 0, 0. So essentially that's just going to be 4, because if I put a 0 in for any of those t values, that's just going to be, leaving me a 4 there. And let's see what we get. So all of the stuff, for s of 6 is going to give me a value of 58 minus a 4. Golly, it's like my head and my brain don't, or my head and my arm don't want to talk to each other today. 58 minus 4, so that would be 54, and we don't have any units or anything, so I don't want to say that it would be, it would be something with time, feet per second or something for velocity. And part C, find the distance that the particle has traveled. Well, the distance in this case can get a little hairy because, all we did there for displacement, it's not really taking into account any kind of, or it's taking into account where we have values that are going to be below the x-axis, where we're moving left as well as right. So that's the displacement. That's where you finished compared to where you started. That's not the same thing as the total distance that you have traveled. So in this case, we're looking for the total distance on part C. So here, where I'm looking for the total distance, that is going to be the definite integral from 0 to 6 of the absolute value v of t dt. And that one is kind of wholly different. Now, as a calculator exercise, this really isn't all that complicated, and I'll go to the calculator here shortly to see what we wind up with when we do this. But if I don't have a calculator, how do I do it? Basically, I have to look at the intervals of increasing and decreasing, or intervals where it's going to be above the x-axis and below the x-axis. So what I'm going to do is I'm going to take the velocity function that they gave me, the 3t squared minus 10t plus 3. And essentially we want to know what are the critical numbers of the velocity function, because when the velocity is 0, that tells you where the function changes direction, and you can, or at least that's going to indicate where the, critical numbers of the velocity function are going to tell you where the position function changes directions, and we can identify some intervals of where it's positive or negative based off of that information. So when I factor this, and I'm not going to, you guys know how to factor, the factors here are going to be 3t minus 1 times t minus 3. And so here I'm going to get t is equal to a positive 1/3 and a positive 3. So those are the critical numbers that I'm going to be looking at. So I'm going to start breaking my function up along that interval, or along those different intervals. So here my distance is going to be from 0 to 1/3 absolute value v of t dt, plus the definite integral from 1/3 to where it changes directions again, in this case to be the 3 absolute value v of t dt. And then it's going to change again from 3 to a 6, 3 to 6 absolute value v of t dt. And we got to figure out, each one of these things here. So I'm going to simplify this somewhat. So here I'm going to say the antiderivative here, this is going to be the s function. So s of 1/3 minus s of 0 plus the absolute value of s of 3 minus s of 1/3 plus the absolute value of s of 6 minus s of 3. And again, use a calculator to do all of these computations, otherwise you're going to be trying to do this stuff forever. In this case, I get an absolute value of 121 over a 27. And I'm going to just make sure that I have common denominators here inside of my brackets. And x of 0 in this case is going to give me a 108 over 27 plus the absolute value of the next interval. Here I'm going to get a negative 135 over 27 minus a 121 over 27 plus the third interval, s of 6 minus s of 3. I'm going to get 58 plus 5 in this case. 58, not 5.8. 58 plus 5. And so here I'm going to wind up with a 13 over 27 plus the absolute value of the middle terms are going to be a 256 over a 27. And the next one you can just say, you can add the 58 and the 5, but I'm, again, just kind of doing this so I can have common denominators. And I'm going to have 1701 over 27. And so all of that works out to be 1970 over 27, or approximately 72.963. Okay. Now this is where, again, if you're fortunate enough to have one, you might want to just go to a calculator and type this into your calculator at the very least to just double check it. Okay. Let's see. So we need to get some calculator here going. You're gonna let me start doing stuff? Nope. Menu, add a calculator. Okay, so here we go. So I'm going to hit the little button next to the book, and I'm going to pick my definite integral right there. And we were doing it, what, from 0 to 6. And I'm going to hit that little button next to the book again, and I'm going to pick my absolute value symbol here. And we're going to take the velocity function that we had, that was given to us, of 3t squared minus 10t plus 3 with respect to t, so dt in this case. And we'll hit enter, and we get the 1970 over 27. So at the very least, we're verifying the process that we did was correct. But this is how you would do it on your calculator if you didn't need to necessarily show all of your discrete steps for the total distance. Excuse me. So let's move on and see if that's the end of that example for the first one. Example number 2 is a pretty popular one. You drop your calculus book from a window 48 feet above the ground. So here, you're, oh, let me get my pencil turned back on. You're in a building, okay? And so let's say that this is the window that you're at, okay? And I guess you're not going to be hanging out of it, but let's just say that, you know, you're going to take your calculus book, right? Calculus book, and you're going to drop it, and it says that you are 48 feet above the ground. So that tells you your initial position. So your initial position, S naught, is 48 feet. How long will it take your book to reach the ground? So how long? That is time. So we got to solve something in terms of time. What is the velocity of the book the instant that it reaches the ground? Okay, so we have two things that we're looking for. We're looking for how long does it take to reach the ground, and what is the velocity of which what it is when it gets there. Okay. So we don't really need to do much in the way of the first part to calculus-wise to actually figure out how long it takes to hit the ground, but the time is going to be useful for the velocity. So the position function, s of t, because the constant for gravity, and in this case they're giving us it in feet. I'm going to use negative 32, or use 32 feet per second squared for the acceleration due to gravity. So in this case, when we say negative 1/2 of 32, that will be negative 16 t squared plus the initial velocity, v naught of t, plus the initial height, s naught. Well, in this case, we know what the initial velocity is, because if you're just holding it above the ground, the initial velocity is 0, so this is just 0. So we have negative 16 t squared, and the initial height is 48. So there is our, essentially, there's our function that we're going to be looking at for the position function, and we want to know how long it took to get there, so we have to solve for time. So set it equal to 0, and that'll give you 16 t squared is equal to 48. Divide, and we'll get t squared to be equal to a 3. So time in this case will be the square root of 3 seconds. So no calculus really on that one. You know, it's just the function itself, like I said, can be found pulled straight out of an Algebra 2 textbook. But what is the velocity? Now here, this is where we have to do a little bit of calculus, and it's not an integration, it's a derivative. We need to know what is the what's the velocity function. So I'm going to take the derivative of the position function, and that'll give me negative 16t, basically plus the initial velocity, plus, where did I go? Nope, I'm not doing that right. Here we go. negative 32t, negative 32t, not negative 16t. I keep getting doing too many integrals and derivatives at the same time here. So in this case, we're just taking the derivative of the function, and so the initial velocity is 0, so the derivative of 0 is 0, so this is the velocity function. So here I'm going to say v of radical 3 is equal to negative 32 times radical 3, and I don't have, I mean, I have a calculator handy, but it's not asking me to do anything. We could stop there and just say, I guess clean it up a bit and say negative 32 radical 3 feet per second in this case, but of course we probably want to know exactly how fast he was going, like in something that actually makes sense to us. So if you take that on your calculator, we're going to get about negative 55.426 feet per second is how fast the book was going when it hit the ground. I mean, again, speed would be the absolute value of that, so, but still pretty fast, 55 feet per second. So next, a potato is launched straight up from the ground, and it reaches its height, its greatest height at 6 seconds. Find the initial velocity of the potato and the value of its maximum height above ground level. Now, a lot of times you'll see a question like this, and again, very straight out of a Physics 1 textbook or an Algebra 2 textbook, something pretty straightforward. Because if you look at it, we have our potato launcher, right? Think of it as, I guess, like a poor man's mortar or something. You take your potato, your little spud here, and you drop it inside, and what's going to happen is it's going to get shot up. And here you are, having a good old time here, just launching your potatoes into the air. And so it launches it into the air, and it's going to go, it's going to have some kind of trajectory like that. And again, this is a lot of times why you'd see it in a physics textbook, but very much going to be thrown into a math textbook at some point. Now, it tells us that it reaches its greatest height at t is equal to 6 seconds. So right here, this is 6 seconds. Now, what separates this as a calculus question versus an algebra question is usually if they're asking you to find the initial velocity, a lot of times not only will they give you the greatest height, but they'll also tell you what the maximum height was. Because if you're looking at your normal position function, right? If you just say s of t is equal to negative 16t squared plus the initial velocity times time plus the initial height, if they give you the height that it got to, you can put that here, like you can put your max height here and take your time that it took you to get there and solve for the initial velocity, because in this case, the initial position, that is 0 because you're shooting it from the ground. But in this case, they're not telling us what the maximum height is, so we have to use a little bit of calculus in this case in order to be able to solve for the initial velocity. But we'll go ahead and change this. That we don't need that because, again, the initial height is 0. Okay, and if I just try to take the 6 and plug it in there, I don't have any position with which to solve it for. I don't have a position that I can put on the left side of the equal sign to help me solve for t. Okay, well, we still need something in terms of time. So here, let's take the derivative of this and let's find the velocity. Because since I understand the relationship between position and velocity, we can write the velocity function, and maybe from the velocity function we can get the initial velocity. So v of t in this case will be negative 32 t and plus the initial velocity when I take the derivative of v naught of t, v naught times t, I should say. Okay, well now I can take that value of 6 and plug it into the function and say, okay, well when the velocity is equal to 0, that's where I'm at my maximum. So we can say negative 32 times 6 plus v naught, and so 32 times 6 in this case is going to be 192, so 192 will be equal to v naught. So we would say 192, and what are we at? Feet. Is that where we're at? Feet? Where's my, I know 6 seconds. It doesn't, I don't think it gives me. Straight up from the ground level, reach its greatest height, 6 seconds, find the initial velocity and the maximum height. So I don't know, I guess we'll just say feet per second. Okay, feet per second. I know they're not really telling me what the length is, but so there's the initial velocity. So find the initial velocity of the potato and the value of its maximum height. So the one thing that if they had given it to us, we could have avoided having to do the derivative for the calculus. But now that we have that, we can find its maximum height. So I'm going to take that 192 initial velocity, and now I can identify the maximum height. So what I'm going to do here is I'm going to say the maximum height was reached at 6 seconds. So I'm going to say S of t is equal to, in this case, negative 16 times 6 squared plus the 192 times 6. And again, guys, I'm not going to try to ask you to do this discretely in your head or off on the side. Use a calculator to get that value. And in this case, you're going to get 576. And again, we're presuming that it's feet. Maybe I'm just not seeing it. 576 feet after 6 seconds with an initial velocity of 192 feet per second. So a lot of these are pretty, not out of the ordinary questions. They don't necessarily need calculus all the time to solve them. So what I want you guys to do here, go ahead and try working out this example and just see what you're able to get. And because this one's not really a fancy kind of question. Go ahead and pause the video, see what you get here. When you're done, hit play. So again, like I said, this one, hopefully you're able to get the answer okay, because it doesn't really require any calculus to solve it. It's just asking you to solve for a particular variable, and it gives you enough information to figure it out without any calculus. They give you an initial height. The initial velocity, as you're just holding it over the ground, is or the initial velocity is 0. The initial height is 60, and just plug in the values and see what you get. And in this case, we wind up with a gravitational constant of 13 1/3 feet per second squared. And here, moving on, this is another one where I'm going to ask you guys to try to pause the video and work your way through them, because this one is going to require some calculus here. And I want to make sure that you're able to think your way through it and see what you're able to get. So the setup, suppose you're driving behind a bus, which often happens at 66 feet per second, 45 miles an hour. You finally get a chance to pass. You step on the accelerator, giving the car an acceleration of 4 divided by the square root of t, where a is measured in feet per second, or feet per second squared. And so here, how fast are you going? 16 seconds after you've passed the bus. How far did you travel during that time? And what was your average velocity over the 16-second interval? So go ahead and pause the video, see if you can work these 3 out here. And when you're done, hit play and check your work with mine. All right, ladies and gentlemen, here we go. For part A, how fast were you going? So how fast, that indicates that we're talking about speed or velocity in some way. So we can take the acceleration function that was given to us, which was 4 over the square root of t, and find its antiderivative, which would in this case be 8 times the square root of t. In this case, we have a constant of integration because we knew how fast we were going at the outset to be 66, so the velocity function would be 8, and I probably should just put the 66 here, plus 66. So at 16 seconds, it means we're traveling at 98 feet per second, or about 66.818 miles per hour, which sounds quite a bit, because you went from 45 miles an hour to it's almost 67 miles per hour. So I don't know, 40 where your buses are going to be at. Maybe that can get you in trouble driving that fast. Anyway, how far? How far is talking about a total distance. So how far did you travel over that interval from 0 to 16 seconds? So in this case, the total distance is going to be looking at the absolute value of the velocity function. So the absolute value of the velocity function, when I take the integration or the antiderivative of 8 times the square root of t, I wind up with 16/3 times t to the 3 over 2 power plus 66t. And we're evaluating it from 0 to 16 seconds, which worked out to be 1,397 1/3 feet. And the last one, what is your average velocity? And on the last one here, the average velocity formula that I'm using is just 1 over the difference of the upper and lower bound, 16 minus 0 in this case, times the velocity function. And so the antiderivative of the velocity function, we're using the same one that we had in the last example, 16/3 times t to the 3 over 2 power plus 66t. And in this case, the displacement and the average velocity, the displacement and the total distance that we traveled happen to be the same thing, which kind of makes sense because if you look at the function, it's going to be continuously increasing. There are no values with which it would be below the x-axis if you look at the actual function. That's not always the case, but in this case, the displacement and the total distance that you traveled happen to be the same thing. So we wind up taking the 1,397 1/3 and multiplying it by 1/16, and that's how I get 87 1/3 feet per second for the average velocity here. So these are going to be much more kind of indicative of the kinds of questions that you're going to be expected to really be able to do, like maybe on an AP kind of test. That last example 4, where you're dropping the tennis ball to find the gravitational constant, probably not so much. Okay, moving on, let's take a look here. And again, this is another perfect example for you guys to try and attempt it yourself, because you have to use some calculus to actually figure out this question. And we've already done a couple of examples that walk you through essentially what we're looking at. So I'm going to ask you, let's review the problem and see what we're talking about, and then pause it and try to work it out. So a particle is moving along the x-axis, so it's giving us a velocity function. Measured in meters per second after t seconds with an initial position of -3. So determine the displacement of the particle over the time interval from 1 to 7. So that's going to be looking at a definite integral. What is the total distance? So total distance will be the same integral, but with an absolute value function instead. And I think there's more to it. There is a part C and a part D. Nope, I'm thinking of a different question. So these are the only 2 questions that we have. So go ahead and pause the video. Try answering these 2 here and see what you get. And when you're done, hit play and check out my work and look how check it with yours, okay? Alrighty, let's see how we did. Determine the displacement on part A. The displacement is just the definite integral of the velocity function. So when you take the antiderivative of the velocity function, we wind up with -1/3 t cubed plus 7 over 2 t squared minus 10t evaluated over the interval from 1 to 7. And we ended up with a displacement of -6 feet. However, the total distance that we're traveling here Similar to what we saw in an earlier example, I'm going to find the critical numbers of the velocity function to be 2 and 5, so that way we can break up the definite integral into separate parts of where it's changing directions. So I have an interval from 1 to 2, from 2 to 5, and from 5 to 7. And over those particular intervals, the absolute values that I got were 11/6, 9/2, and 26/3. And when you add all of those up, I got a total distance of 15 feet. So the last couple of examples that we're going to take a look at in this lesson, they're going to take a graphical and, in this case, a tabular approach. So a city bus accelerates as it leaves one stop, and then it decelerates as it comes to another stop. The chart below measures the velocity in miles per hour between each stop. And so part A is asking you to find the distance in miles the bus travels between every stop using the trapezoid rule. So essentially, let's just kind of look at these first ones here just to show you why we're kind of looking at the trapezoid rule. Okay, so if we were to take those points and plot them, I would have a point at 0, 0. I would have a point at, let's just say, 5 and 18, and then at 10 and 6. Okay, so the first interval from 0 to 5, that's essentially going to give me this kind of triangle shape here. Okay. Well, if I continue from 5 to 10, I'm going to have, in this case, I have a trapezoid. And that's kind of what they're looking at, where the vertical segments are going to be the parallel bases, and the change in x is the height of the trapezoid. Okay, so that's why they're saying use the trapezoid rule here. Okay, so here, find the distance for between each interval. For the first one, it's really just a triangle. The height of one base is 0, so let's look at the first one here. First of all, the distance that I travel at the first part is 0. So we're looking from 0 to 5 minutes. How far did we travel? So from 0 to 5 minutes, I'll keep doing that one in blue here, where we would have 1/2 times the sum of the bases. So the first height of the base is 0, plus the second height of the base was 18. And so 1/2, that's coming from the trapezoid formula, or that's just the, what the trapezoid formula is. So what is the height? The height in this case, what did they give us our dimensions in? Let's see, we're looking at time in minutes, but they gave us our velocity in hours. Okay, so we have to do a little bit of a conversion here. So we know that there's 5 minutes, or we went 5 minutes, and there's a total of 60 minutes in an hour. So that would be equivalent to 1/12 of an hour. Okay. So since they're giving us our time in minutes, but our velocity in hours, we have to do a conversion here. And so I'm just converting the minutes that they gave us from our table into hours. So this would be 1/12 of an hour. That's the delta x here. This is the 1/12. That's the height of the trapezoid or the triangle, however we want to think of it. So 1/12. There, 1/12. So that would be 1/24 of 18. Which when I just did it on my calculator, and I got 0.75. So that was the distance that it traveled, was 0.75. And so now let's take a look at the next one. And I'm going to have you guys try and do some of these. I'm not going to work out every single one here. So the next one I'll do here in green, and that'll be from 5 minutes to 10 minutes. So from 5 minutes to 10 minutes, the time is the same. So the delta x, the height of the trapezoid, will still be 1/12. That won't change. So I'll say 1/2 times the sum of the bases. So I have one base that's 18, and I have one base that was 6, and the height here, this part here, that's still 1/12 because we only went 5 minutes again, so that's 1/12 of an hour, 1/12. And so 1/24 of 24 is just 1. So we traveled 1 mile there. So we went from 3/4 of a mile to 1 mile, and I'll do one more for you and then have you guys try and finish off the rest and just see how you do. So now we're going to be looking from 10 minutes to 20 minutes. So our time interval is changing here in this case. So if we're saying we have 10 minutes out of the total 60 in an hour, that is 1/6 of an hour. So that's going to be our delta x now. So if we kind of kept going with the graph here, and I don't expect you to, but on the next one here, we went to 20 minutes. So this is our delta x. That's going to be 1/6 of an hour. And we had a height of 6 and then a height of 32. So we kind of have this trapezoid right there, kind of in that pinkish color. So here, half of the sum of the bases, in this case, would be half of 6 plus 32. And the time here is 1/6 of an hour. So that's the base of the trapezoid, or the height of the trapezoid, really. And in this case, 1/12 of 38 is going to give me 3.167 miles. Okay, or as a fraction, 3.167, I got 19/6. 19/6. Okay, so 19/6, or the 3.167, whichever you prefer. And we would just kind of keep doing that, and I pause the video and make sure that you can actually get the rest of them, but let's go ahead and just fill these in here because this is just a tedious operation at this point. So the next one I got to be 1.5 miles, 5/3 of a mile, or 5 1/3 of a mile, or 5 2/3, I should say. Then we got 4, and then I got 4 1/4, and then I got 11/12 of a mile. Okay, so that's all of part A, where we're just, identifying the heights of the trapezoids, the vertical segments, and understanding that delta x is changing, but pay attention that they're giving us different units. We do have to convert the units to work with our miles per hour. So find the total distance that the bus traveled in 60 minutes. So the total distance is just the sum of whatever those values that we got there, because that's what we did, is we traveled for 60 minutes. And the sum of all of those, I am getting 17.25 miles. And just type them on a calculator and get the sum that way. So this last one here is giving it to us graphically, and it's in 4 parts. The graph at the right represents a velocity function of a particle that is moving along the x-axis on the time interval from 0 to 8 seconds in this case. For what interval or intervals of time is the particle moving to the right? Justify your answer. And I definitely think that at this point, these are questions that you do need to attempt on your own, because these are very typical types of questions that you could expect to see related to this material on the AP exam. So go ahead and try and answer part A and B. If you have the notes, you can probably just kind of follow along with C and D on your following along with this, but they're not fit on this slide here. So go ahead and try working A and B, and when you're done, hit play and check your work with mine. Okay, and see how did you do. So for what interval or intervals of time is a particle moving to the right? The particle moves to the right on the interval from 0 to 3 seconds and from 7 to 8, because that is where the velocity is positive. That on those intervals, that's where the velocity is positive. Part B, on what intervals is the particle slowing down? In this case, the particle is slowing down on the time interval from 2 to 3 seconds and from 6 to 7 seconds, because that's where acceleration and velocity will have opposite signs. So you see that velocity from 2 to 3 is still positive because it's above the x-axis. However, the slope at that point, its derivative, the acceleration, is negative, and that is where it justifies that we're having something that is slowing down. So here are the last two. Go ahead and try answering these questions on your own, and when you're done, go ahead and check your work with mine. But here, when the particle is stopped, when is the particle stopped and changing directions? Justify your answer. So in this case here, I'm saying the particle is stopped and changes directions at when x is equal to 3 and when x is equal to 7, because that's where the velocity is equal to 0 and it's changing from positive to negative. And finally, on what time interval or intervals is the acceleration 0? Justify your answer. In this case, the acceleration is 0 when the velocity is constant. So the velocity is constant along the time intervals from 1 to 2 seconds and from 4 to, and I think that's a typo. I think it should say 7. I'm sorry, 6. I believe that's now that I'm looking at it, I think that's a typo. I think that should be 6. So from 4 to 6, because that's where the velocity is constant, so its acceleration, the derivative is 0 at that point. So from 1 to 2 and 4 to 6. And that's going to kind of wrap it up here for what we're talking about for particle motion and how we're applying it with integration. If you have any questions, of course, get in touch with me and let me know. I'll be happy to help you. But until next time, guys, hope you're all healthy and happy, doing well. Take care, and we'll see you soon.